An ant of mass m clings to the rim of flywheel radius r as shown above. Ant, yeah, this ant here. To the rim of flywheel radius r as shown above. The flywheel rotates clockwise on horizontal shafts S. Horizontal shaft S. Here, with the angular velocity omega in this direction. As the wheel rotates, the ant revolves past the stationary horizontal shaft S. Okay, meaning the ant passes this point, huh? Stationary point 1, 2, 3, and 4. The ant can adhere to the wheel with a force much greater than its own weight. Okay. It will be most difficult for the ant to adhere where the wheel is revolved past which of the 4 points. That's definitely the bottom, huh? Because at the bottom, the weight pulling the ant down is downward, and inertia of its own, because it has mass, it tends to be thrown downward away from the center of the rotation, and therefore at the bottom, which is the point 3, the ant will be most likely to fall out. Okay.
Yes.
3. What is the magnitude of the minimum adhesion force necessary for the ant to stay on the flywheel at the point 3? Minimum adhesion force. Okay. This question 8 is actually not difficult. Pretty simple. You just need to use the centripetal force, FC, centripetal force, which is mv squared over the radius r, or another formula, m times omega squared times r. Remember, we did it last time in Physics 1.
Yes.
This centripetal force is equal to the force that the ant adherent to the wheel, which is the force by some chemical substance on the leg of the ant that help it to stick to the object, huh? And then subtract the weight. Yeah, subtract the weight, and therefore we can find this one, huh? Fa. So Fa is FC, which is m omega squared times r, and then add the weight, huh? Mg. That's it. Meaning the answer E is correct, huh? Yeah. The same formula. No r squared, huh? Just r.
Yes.
Question 9. A turntable that is initially at rest is set in motion with a constant angular acceleration alpha. Turntable that is initially at rest set in motion with a constant angular acceleration alpha. What's the angular velocity of the turntable after it has made one complete revolution? Angular velocity, one complete revolution, meaning the time is the period. P here, the period. Angular velocity, constant angular acceleration alpha. Okay, good. S v squared equal u squared plus 2as. Huh? We have omega squared equal omega 0 squared plus 2 times of alpha angular acceleration times the angle that it rotates, and one complete revolution, meaning that this theta, the angle is 2 pi. Okay, with omega 0 is 0, and therefore we have omega squared equal to 4 pi times alpha, and therefore omega is the square root of 4 pi alpha, meaning answer C. Okay. Okay.
Yes.
Excuse me for 1 minute. I need to reply a message. Okay. Question 10, huh?
Yes.
5 kilogram sphere is connected to a 10 kilogram sphere by a rigid rod of negligible mass. Here on this diagram, as shown above, the sphere rod combination can be pivoted about an axis that is perpendicular to the plane of the page, and that passes through one of the 5 letters points. Which of the points should the axis pass for the moment of inertia of the sphere rod combination about the axis to be greatest. Okay, to be greatest. That should be the point D. Let's check my prediction first before I explain why, huh? 10. E, answer E, not D. The point E. Oh, okay. The moment inertia to be greatest. Again, the formula for the moment inertia is the sum of individual mass and the square of individual distance to the axis of rotation. For example, if we choose the point B here to be the axis of rotation, then the moment inertia through that point B is 10 kilogram on the left, times the distance AB square. Okay, and then add it with the 5 kilogram times the distance BE square. Okay, and then repeatedly you calculate the moment inertia compare when you choose different point to be the axis of rotation, meaning that the system rotate about this point C. Okay, and then yes, after writing the 1, 2, 3, the 5 equation, we will compare which one to be the greatest. For example, if I choose the point A to be the axis of rotation, then the distance AA is definitely 0, and therefore the moment inertia will be smallest when the axis of rotation is A, passing through A. Okay.
Yes.
Yeah, check that formula for the exit here, the formula here, mr squared. Yeah. So when the exit passes through E, it will be the greatest. Yeah, the answer is E, the greatest, because the distance from A to E, the 10 kilogram is greater than 5 kilogram. And with the exit of rotation chosen to be E, the distance will be maximum for the moment of the 10 kilogram, huh? Okay.
Yes.
11. A wheel of with rotational inertia is mounted on a fixed frictionless axle. Wheel. The angular speed omega of the wheel is increased from 0 to The angular speed omega of the wheel is increased from 0 to omega f in a time interval t. Angular speed of the wheel is increased from 0 to omega f in a time interval big T. What is the average net torque on the wheel during this time interval? Okay, average net torque, similar to equation F equal ma. We have the torque will be equal to the rotational inertia I times the acceleration, angular acceleration. Angular speed. The question, angular speed. We're given, okay, the period in a time interval t. Okay. So alpha here is a constant which can be calculated by omega minus omega 0, which is 0 over the time, the period t, The period t. And the torque, we don't know the torque. Time interval here is the period, not the torque. Okay. We don't know the torque here. Average net torque. Okay, we're calculating it. Okay, so the answer is this one, I times omega over t. I times omega over t, which is for answer I times omega over t, E, Okay.
Yes.
I times omega. Omega here is mean omega final after one revolution over t. Answer E. Yeah. 11 E. This book again, 136. This is the cover of the books. It's a collection of all the past paper questions. Therefore, I urge you to try solving all the questions in this book. Huh? And as you see that if you keep practicing not only this book, but other book as well, the Princeton book, and if you finish that, I will send you some more documents. It will be finally not that difficult, will be easier. Question 12. What is the average power input to the wheel during this time interval? Power input, power. What's the formula for power in rotational motion? Again, it's still energy over time, huh? That energy is kinetic energy. Kinetic energy over time. And that kinetic energy is the rotational kinetic energy, not the normal 1/2 mv squared, but the 1/2 m, which is I, huh? Omega squared. This is rotational kinetic energy, okay? 1/2 I times omega squared over the time. The time is the period t, okay?
Yes.
So we put the number 2 to the bottom. So we have I omega squared over 2t, which is b. 12b, yeah. Again, similar to AP1, the multiple choice still easier than the free response. 13. 2 blocks of joy-like string that passes over the pulley shown above, which has the radius small r, big R, sorry, and the moment inertia I about its center. Moment inertia I about its center. Okay, the moment of inertia of this pulley, huh? T1 and T2 are two tensions in the string, and definitely two T2 on the string either side of the pulley. T2 is down here. It must be greater than T1, huh? So that the torque generated by T2 in the clockwise direction is greater than the torque of T1 in the opposite direction, making the pulley to rotate in this direction. Okay. So T2 must be definitely greater than with T1. Which of the following equation best describe the pulley rotational motion during the time the block accelerate? Okay. Rotational, similar to the equation A equal to F over M, huh? Mass. We have angular acceleration alpha equal to the torque, total torque, the net, the resultant torque, divided by the rotational inertia I. So the torque is alpha, the torque is the T2 times the radius, and then minus T1 times radius, huh? And divide the moment of inertia, which is I, given, okay?
Yes.
And therefore the answer is T2 minus T1 times R equal to I alpha, answer D here. 13. Is that 13? Yeah, 13D. Yeah, correct. Uh, 14. A disk is free to rotate about an axis perpendicular to this through its center if the disk starts from rest and accelerates uniformly at the rate of 3 radians per second squared. For 4 seconds, its angular displacement during this time is angular displacement. Start from rest, meaning omega 0 initial angular speed is 0. Uniformly, meaning that the acceleration is constant. The rate, which is radian per second square, this rate is the alpha, the angular acceleration, okay? It's the time. The angular displacement, again, we use the formula theta equal to omega 0 times t plus 1/2 alpha t squared. Similar to the equation S equal ut plus 1/2 at squared, huh? Okay?
Yes, sir.
Omega 0 is 0 here. Acceleration alpha is 3, given 3 radian per second square, and the time is 4 seconds. 4 square is 16. 16 over 2 is 8. 8 times 3, 24, huh? Yeah, 24 radians is the answer. The question 16, 15. Solid cylinder mass more n and the radius r has a string wound around it. A person holding the string pulls it vertically upward, as shown above, such that the cylinder is suspended in midair for a brief time interval, delta t, and its center of mass does not move. Holding the string pulled it vertically up, cylinder suspended in midair, rolling without the center of mass, which is the center of this cylinder, remain there. It's difficult to achieve something. It's like what's it called? The yo-yo game. You know that thing? Yeah. Somehow, if you rotate it correctly with the correct speed, the position of the yo-yo remain the same. It rotates, but the position of the center O here, the yo-yo suspends in midair. Okay.
Yes.
Brief time interval, the tension is T, and the rotational inertia of the cylinder is 1/2 mr squared. The net force of the cylinder during the time interval delta is, the net force is 0. Answer is simply that, 0, because it is suspended in midair, meaning that its acceleration is 0. Translational acceleration, which is A, the normal acceleration is 0, Okay.
Yes.
0 net force, meaning that the tension upward is equal to the weight downward. The tension here is equal to the weight, equal in opposite direction to the weight. So answer is 0. 15, E, yeah, 0. 16, the linear acceleration of the person's hand during the interval T is linear acceleration. Meaning that we need to calculate this one, but it's supposed to be 0. So the answer is 0 as well. 16, B, cylinder sub 70 miss air. 2G, no, answer is not 0. Wait. Oh, sorry. The net force is 0, but the acceleration is not 0 because the object is rotating. Even though the force is 0, but the acceleration is still different from 0 because this is rotation, not only the translational motion like a block sliding on a surface. Okay.
Yes.
Yeah, acceleration is still different from 0, and we need to find it. Again, to find that acceleration, we use this formula, angular acceleration alpha times the radius. This angular acceleration is equal to the total torque, divided by the moment inertia I. Okay. I is given already, which is 1/2 mr squared here, equal to I. So we need to find the torque. The torque compared to the axis of rotation, which is the center, and therefore the torque here is simply just the tension times the radius. Okay, tension times radius, and then divide 1/2 of the mass times r squared, and then times I squared. So we simplify the r, r times r and over r squared. So the answer is 2t over m. 2t over m. And because t equal to the weight, t equal to the weight, so that is 2 mg mg over m, and therefore that equal to 2g, and therefore it is answer B. Because this tension is equal to the weight, mg. Okay. 17. A block of mass small m is placed against the inner wall of the hollow cylinder radius r that rotates about the vertical axis with a constant angular velocity omega as shown above. In order for the friction to prevent the mass from sliding down the wall, the friction must be upward. And that friction is the coefficient of friction mu times the normal force that the wall exerts on this object. That normal force is equal to the centripetal force Fc, which is m times omega squared times r, the radius. Okay. Yes. And therefore the friction, Fr, friction, is the coefficient of friction times m times omega squared times r. satisfied with the following inequality. It must be at least equal to this one, and therefore the answer is we need to find this coefficient. Okay, so FR, okay, and FR is at least equal to the weight, huh? Okay, FR equal to this thing. It must be at least equal to the weight mg. Therefore, we can simplify m, and mu resulting in mu greater than equal to g over omega square r, huh? Omega square r g, this which is d here. Okay. 17 b. G over square. Wait. This is smaller. I'm wrong choosing. This is rector. Huh? Yeah, rector. Okay.
Yes.
Question 2. A wheel of mass m and radius r rolls on the level surface without slipping. If the angular velocity of the wheel is omega, what is the linear momentum? Formula for linear momentum is linear momentum L equal to I times omega, just like P equal mv, huh? I times omega. Given I of the wheel is 2 over 5 mr squared. The question about, huh? Or you have to memorize this one. Again, I will send you the 3 formula for 3 things yesterday, huh? Try memorizing those 3 formula for moment of inertia I of the 3 type object. Sphere. The sphere is rotational inertia. Not super here. 3 things here. The cylinder 1/2 mr squared. The sphere 1/5. Okay, sphere 1/5. So cylinder should be 1 over 4, 1 over 12, depending on the axis of rotation. Cylinder. Cylinder. Okay, cylinder here 1/2 mr squared. Sphere 2/5. What are we doing? The wheel. So that should be 1/2, huh? 1/2. Linear momentum I times omega. So this is the answer. 1/2 m omega r squared, which is, this is r squared, not r. Wait, omega squared, not omega, huh? Linear momentum. There's no answer. Question part 2 A. M omega r. Angular velocity omega, linear momentum, wheel mass m, radius r. M omega r. My answer is 1/2 mr squared times omega. Rotational inertia of a cylinder. Of a wheel. Okay, check a wheel. Inner and outer. It is solid wheel. Solid cylinder is 1/2 mr squared. Moment of inertia, here the formula I times omega. I times omega. V equal omega r. Okay. Linear momentum. Oh, question is linear momentum, not rotational momentum. Angular momentum. This is angular momentum. Sorry. The question is linear momentum, huh? So linear momentum is simply P equal mv, and V is omega times r, huh? The mass is big M, so the answer is m omega r. Simply A. Linear, not angular, huh? Angular momentum is L equal I times omega. Angular momentum is the momentum in the rotation. Okay.
Yes.
Question 3 and 4. The sphere mass m radius r rotational inertia I released from rest the top of the incline shown above. If the plane is frictionless, what is the speed of the center of mass of the sphere at the bottom of the incline? As I remember, in the case of the frictionless surface, the object here does not rotate, but only slides, and therefore we just use the formula mgx potential energy equal to 1/2 mv squared at the bottom, meaning that v will be the square root of 2gh, which is a, huh? Hopefully that my memory is correct. Yeah, correct, a. So the point is that to remember, in the case of no friction, the object does not rotate, and we do not need to involve the rotational kinetic energy. 1/2 I omega square. Omega here is 0. Okay. Only the linear kinetic energy. Okay.
Yes.
Question 4. If the plane has friction so that the sphere rolls without slipping, what is the speed of the center of mass at the bottom of the incline? Typical question. Okay. Again, for this kind of question, we did a kind of similar question last time. Mg equity potential energy equal to 1/2 mv squared, which is the linear kinetic energy, plus 1/2 I times omega squared rotational kinetic energy. Huh? And I of a sphere is as I remember, like 2/5. Yeah, 2/5 of mr squared. Huh? 2/5 mr squared. Try solving this equation and find the speed v. Huh? And another relationship, omega is v/r. Now I would like you to do it yourself, simplifying this equation, replacing omega to be v/r, huh? And I to be 2/5 of r squared to find the speed v. Find v here. Okay.
Yes.
And after solving that equation, tell me the answer that you choose, A, B, C, D.
Answer D.
D. Check it. Question 4. Answer is E. Check again your calculation. Made mistake somewhere. 2 more minutes, huh? If you still cannot find the mistake, and I will solve it. Question 5. A wheel of 5.5 meter radius rolls without slipping on a horizontal surface. The axis of the wheel advances at constant velocity. Axle of the wheel advances at constant velocity, moving distant 20 meters in 5 minutes. The angular speed of the wheel about its point of contact on the surface is. Angular speed omega is simply the normal linear speed v over the radius, and v the distance advances. Does it mean that it constant? Okay. And v here is simply 20 meters divided 5 seconds, huh? 20/5, which is the v, and then divide the radius, which is 0.5, huh? So 4/0.5 is 8. Answer is 8 radian per second. Okay.
Yes.
Answer question 5C. Yep, 8 radian per second.